Today we talk about model calibration in DSSAT 4.6 using Gencalc. In other words, we will determine the cultivar coefficients using measured data. The first thing we need to do is to prepare the cultivar file. We need to edit the file that contains the cultivar coefficients for the species we are interested in, and the species, all the genotype files are included in the folder genotype below DSSAT 46. In that folder, we will look for the file for the species that we want. For instance, for sorghum, we will edit sg-ser, which means sorghum ceres 046 for DSSAT 46 .cul. In that file, we need to do two things. If there are not maxima and minima cultivars that contain the maximum and minimum values for each parameter, we can add them. These would be fake cultivars. They are not existing cultivars, but fake cultivars that include the extreme values for each parameter. We need also to add a new cultivar with best guess parameters for the new cultivar that we want to calibrate. Using a file editor, a text editor like context, we go and look for cer046.cul, which is this file that we have here. And as we said, if we don't have already the minima and maxima cultivars, we create this. With that, when the calibration program runs, it will run between these limits for each of the different parameters. For instance, for P1 we had a variation from 100 and 600. P1 is the duration of the time from seedling emergence to the end of the juvenile phase in growing degree days. Apart from that, we're gonna create a new cultivar. For the example today, we will create a cultivar with number IB0056, and the name is gonna be Pioneer 8501. We had already a Pioneer 850 with these parameters, and we will assume that 8501 is the same to start with. So the program will start using these parameters as an initial guess. Once we are happy, we go and save the file. The second thing we need to do is to add the measured data, and we will see an example for grain sorghum. We have taken the data from Farrea and Fassi, comparative response of maize and sorghum to deficit irrigation in a Mediterranean environment, which was published in Agricultural Water Management. To add measured data, we use the experimental data tool in DSSAT 46, and at least typically we would need anthesis and maturity data if we want to calibrate the development coefficients, and at least yield, measured yield, to calibrate the growth coefficients. In that experiment with sorghum, they had different treatments of irrigation, from the best irrigated treatment to the less irrigated treatment. These are the dates for anthesis, the dates of maturity, harvest yield, kilograms per hectare, total weight at harvest, total biomass at harvest, and maximum leaf area index. We open DSSAT 4.6 and click on experimental data, and then we have here a working area. First, with the wizard, we can define the number of rows and columns. the number of rows is going to be equal to the number of treatments, which are 6. And let's think about 5 different variables. This is going to be an A file, which is what we need to do the calibration. T files are for evaluating the model during the season. So T files mean temporal files, which are variables that will measure several times during the season. This is going to be for grain sorghum. Click on grain sorghum and click OK. Now we have to define which is which in these columns. We go click here, and in properties we assign the variable. In this case is the treatment number. We click OK, and the treatment number goes from 1, 2, 3, 4, 5, and 6. The second column is going to be the anthesis date. We click on properties, click here, anthesis date, day of year. We click on OK. What else do we have? We have maturity. Here, click here, properties, and we go for M, and for maturity date in day of year. This following one is going to be harvest. So we click here, properties, look for HW measure. Yield harvest at maturity. We click on OK. We click here. We need the total weight at harvest. Click here, properties, and this is total weight. Well, use the variable name, for instance, total weight at harvest. Click on OK. We need still to add, for instance, if we want to add maximum leaf area index, we would go here and add a new column, insert a new column here, and this would be, for instance, the properties, and then go and use L for maximum light, LAIX. We click on OK, and then we only need to fill the data. Look at this, we have here 205, and the second is 242, and the harvest is 85,538, and 18,377. This is in kilograms per hectare, and the maximum life is 3.36. We continue in inserting the data here. Once we're happy filling the data, we go to File, and then say File As, and then we use four characters like SIAC, means the Agricultural Research Service at Zaragoza, Spain. 9501, 95 is for the year and 01 for the experiment. We can call it whatever we want, for instance 30, and it is a SGA for sorghum and type A file with measured data. We click on Save, and then we're good to go. Then we click and close. We exit the experimental data program. Okay, click on Save, and then we're done. The next step is to enter the management and environmental data for the calibration experiment using the tool Crop Management Data. There are two important details to be considered here. First, in simulation options, it's important to set the output files to default. If we don't do that, we won't create an evaluation .out that is required for the calibration program. We need also to select the new cultivar that we have created, that the one that we want to calibrate. We go to DSSAT and then click on crop management data. I'm gonna show a file that I have created for sorghum. It's called DSSAT 9501, and that includes the experiment by Farré and Fassi. As I said, in simulation options, in outputs, it's important to set output files to default. Leave overview, yes. Summary, yes. And, well, the details are not that important. We click on OK, and in management, cultivars, we have selected Pioneer 8501, which is the new cultivar that we want to calibrate. In this case, we have the 6 treatments using the same cultivar in the same field with the same initial conditions, the same planting conditions. Let's see the planting conditions are plant population of 21.7. The planting date is May 17th, 1995. Row spacing 75. Then the amount of fertilizer is split in 3 applications and changes a little among different irrigation treatments. So the less irrigated treatment receives less water than the best irrigated treatment. Okay. In simulation options, it will use the measure weather data, which are already included in the DSSAT 4.6 package. These are weather data from Zaragoza in the 1990s. This is why we said that the fertilizer treatment changed with the irrigation, and the irrigation management is defined for each of the different treatments with applications every 4th day, going from 6.1 to treatment 1 to treatment 6 that receives the less water per application. Click on OK. And this is the file that we will use for the calibration. Once we're happy with that, we save as. We use 9501 for this experiment. The extension is SGX for sorghum experiment. We had already saved that. Then we click on exit. The next step before performing the calibration is to edit the file that contains the rules of calibration. This is a general file that serves for all crop models in DSSAT 46, Gencalc 2.rul, and it's included in the folder Gencalc within Tools within DSSAT 46. In that file, we will choose what are the variables to be used for the calibration. For instance, if we want to use the flowering date, and for each variable that we will use for the calibration, we will select which crop parameters are going to be calibrated. In general, for development parameters, we need at least anthesis date. And it is recommended to avoid using treatments for calibration with severe deficits for nitrogen or water. So using a text editor like Context here, we go and open this file, which is located in Tools, Gencalc, within DSSAT46. And here we have the different parameters. First, we have general controls here, like here. This line refers to all the crops. And then we have a specific for each crop model. For instance, this is for the series wheat. This is for the alternative wheat model. And we go down, we roll until we find the crop we are interested in. Go and we get sorghum. Here we have the exclamation mark, means that this line is ignored. We only don't have exclamation marks for ADAP, which is anthesis, and MDAP, which is maturity. It means that it will use the time from sowing to anthesis and the time from sowing to maturity to perform calibration. So we are only calibrating for development. For each variable, like anthesis, here we have first 3 values that have the step, the coefficient. P1 would be the genetic coefficient P1, and the loops is 3. This all refers to P1. Then for P2O, we have also 10 and 3. For P2R, which is another coefficient, we have 10 and 3. And for P3, we have 10 and 3. We can leave that like that. Then, for maturity, we can estimate P5, which is the time from anthesis to physiological maturity. And the coefficients and the parameters step and loops are 10 and 3. These parameters are related to how the model will change from one run of the model to the next. So the model will be looking between the maximum and minimum values for each parameter, like P1. And these two parameters tell the model how to change from one run to the other. Once we're happy with this, here we have selected variables, and for each variable, which parameters to calibrate. Then we click on Save, and then we can proceed to do the calibration. We go back to DSSAT 4.6 and we click on Genotype Coefficient Calculator, and then we click on Start Gen Select. We click on OK. This is only a warning, and we look for grain sorghum. We see here IF0056 Pioneer 8501. This is the new cultivar that we want to calibrate. We click on Go, and here we have the different treatments of experiment 9501. I have another experiment, but let's ignore this experiment. We can then select different treatments. It's better to just click on the best irrigated treatment to avoid conditions of water stress. We click on Go, and then it tells us that it will create a batch file called Pioneer /8501. Click on Save, click on Yes if there is another cultivar batch file with the same name, and when we click on Run Gencalc. Then we have this that allows us first to check runs completed. The number of lines is okay. Okay to proceed. Then in action we click on Run. It will now attempt to run all the simulations. We click on Yes, and the model is running. Every time it runs, it increases this number by 1. After some time, the model stops and gives us a message Says end of run appears only partially successful because the number of reruns reached the maximum for one run. Well, now we need to examine the results file, and if we are happy with those, then we will save. We click on Files, and in Model Outputs, in Evaluate, we can see the final run. Click on View, and then we see that the simulated date of antithesis is 70, and the measured value of antithesis is 66 days after planting. For the maturity, we have 103, well, which is very reasonable. Also, although it is not used for the calibration, we see that the harvest, the yield is not far, the measured value of yield is not far from the simulated yield. And also, the maximum leaf area index is close to the simulated value, 522, is not too far from the measured value. Let's say that we are happy with these results. If we are happy, then we go to coefficients, we go to the main cultivar file. We have two possibilities: manually edit or automatically insert run results. We will use this. We'll attempt to aggregate coefficients for this cultivar in the file, the general cultivar file for grain sorghum in DSSAT 46. Click on Yes, and then we can have a look at the cultivar file. We'll reload because it has been changed, and we see here that the new Pioneer 8501 has these coefficients as presented here. The older values, if you remember, they corresponded to Pioneer 850, are copied here just for reference. So these are the starting values of the genotype coefficients, and these are the final values after calibration.